Hi everyone, it's Mr. Pope from Wilmington Grammar School for Boys, and this is the ninth session in the algebra and number theory stuff that I wanted to talk about. And today we're going to be talking about hyperbolic functions. So, just for the record, we're now in the ninth week of me making these videos, and we've long overshot A-level maths. I'd just like to say that it's not a fully comprehensive, know all this stuff and you've got A-level maths. There's a few things that I've missed, particularly sequences and series, functions, that kind of thing. And I'm going to be going over them fairly soon, but in a slightly different context and in a more general context. I feel that A-level maths talks about those things and doesn't really go into enough detail. It's not that I don't find them important, I find it all important. But for me personally, if you have gone through all 9 weeks so far and you've banged out all of the algebra and number theory stuff, the geometry and vector stuff, the calculus stuff, and you've done, the first 4 or 5 weeks of the mechanics and probability and statistics stuff, then you're well on your way. I don't see how you wouldn't get an A star if you completely understood those things. If anything, I'd argue that the matrices and the 3D vector stuff, in particular, or the matrices stuff, wouldn't be in A-level maths. So really, the first half of the geometry and vector stuff you'd only really need. And in actual fact, you'd only need up to the calculus 7 videos, because integration by substitution is in there, but volumes of revolution isn't. Used to be, but it's not anymore. So at this point in time, if you've kept up so far, you've probably done all the main bits of A-level maths, and you're carving a massive chunk into further maths. In terms of the decision maths, if you've caught up to this point, so you've done the decision stuff 1 through 8, then you've definitely finished all of D1. That's pretty easy, straightforward, and by the time we get on to, where is it? The week beginning the 27th, so what will that be? 9, 10, 11, 12, 13, 14, 15. So if you get up to decision 15, you'll have done D2 as well. And then from now on, until the end of this course, I'm going to be looking at step questions as well. Maybe some MAT questions, the mathematical aptitude test, although I don't particularly find them particularly difficult, and I think if you've just been doing the course, they shouldn't be that much of a problem. I just find step more interesting. The problems are bigger, juicier, tend to be better structured, that kind of thing. But yeah, it's much of a muchness. Let's just crack on with hyperbolic functions. So let's recap. The trigonometric functions, are stuff like sine of x, cosine of x, and tan of x. And let's make them thetas, right, to denote angles. And they're pretty much defined in the following ways. You've got sine of an angle is opposite over hypotenuse. You've got cosine of theta is adjacent over hypotenuse. And you've got tan of theta as the opposite over the adjacent of a right-angled triangle. And if I was to draw a general picture of what's going on, then if I've got my coordinate axes like this, and I was to draw a circle with radius 1, so it intersects all of here and here, then if I was to draw a radius like so, and drop a vertical, so that's 90 degrees, and this was theta, then that would be 1, and we would have that x equals cosine theta here, and y equals sine of theta, and backwards and forwards we get the result that x squared plus y squared equals 1 from Pythagoras, but also that sine squared theta plus cos squared theta equals to 1 as well. Okay, so this should all be recap of the trigonometric functions. Now, sometimes these trigonometric functions are also called circular trigonometric functions because they derive essentially from a circle. And hyperbolic functions are also called hyperbolic trig functions because they're kind of analogous, but this time instead of a circle we're going to be looking at a hyperbola. So we're going to define them much in the same way, except there's going to be a few little tweaks. One, if I was to draw what's going on in terms of an xy axis, this time the function that I'm going to be interested in is x squared minus y squared equals to 1. And now, if I think about this very carefully, it's going to cross the x-axis at 1 and minus 1, because when y is 0, x squared equals to 1, so x is plus or minus 1. And it's never going to cross the y-axis, because that would mean if x was 0, then minus y squared equals 1, which y squared equals to negative 1, and there's no real solutions to that. So that's not going to work. However, if I was to play another trick and let y squared equals to x squared minus 1, I notice that as x tends to infinity and y tends to infinity, then this function looks like y is approximately equal to x. Okay, so that means there's going to be asymptotes on the y equals x line, like so. But also, because it's squared, I could have pulled the same trick. We could have said as x tends to negative infinity, then y also tends to infinity. And conversely, when x tends to infinity, y could have been negative infinity. So not only is the y equals x line an asymptote, by symmetry, the y equals minus x line is also an asymptote. Oh mate, come on. My robot hoover's going off again. Right, where was I? Okay, so I know all these things about this graph, and I know it's going to behave like these lines. So I can deduce actually that it's going to go like that, and then hug the y equals x line and get infinitely close, and it's going to go like this by symmetry, and it's going to do the same this side and this side, so it infinitely hugs those asymptotes. So now we do the same thing, okay, and that is, imagine a line from the origin that points, that's straight up, and it meets a general point on that coordinate axis, and we're interested in this weird triangular-like shape. Now it's clearly not a triangle because there's this curved bit here. Now this area here is going to correspond to this area over here. Okay, there's the analogy. And once we do a little bit of De Moivre's theorem, and once we know how to do some other calculus type things, when we look at conic sections in a little bit more detail, you'll be able to see where all this stuff comes from. But for now, if we call sine of x now, well, what is sine of theta but sine of theta, right? So this is important. So it's like sine, but it's the hyperbolic sine of theta. Now there's a h here. Now some people call it shine, some people call it cinch, like that was a cinch. Some people call it hyperbolic shine. It doesn't particularly matter. I call it shine, even though that's probably widely looked down upon, and people would have put it as cinch. But yeah, I'm just going to call it shine. Now sine is defined to be e to the theta minus e to the minus theta all over 2. And now this will start to look incredibly familiar when you know a little bit about de Moivre's theorem. And just as a side note, it's going to be very rare that I prove things unless I deem that proof is particularly interesting or it's not necessarily intuitive. If I just gloss over things and say, well, this is this because of this, I will probably say it is this because of, and then state the theorem or rule or theorem or law or whatever it is that links to it. And then I encourage you always to go away and prove it yourself. The reason why I'm going to gloss over these things is because, you know, if I stopped for every proof like this and it took 20 minutes per proof, I feel my videos are on the hour to 2 hour length anyway. So I'm actively looking for ways to kind of cut them down. And I know me talking about cutting them down is a little bit ironic, but essentially, if you want to see where sine, cosh and tangent come from, and I'll do them quickly, cosh of theta is e to the theta plus e to the negative theta all over 2. And tangent of theta, right, this is cosh, this is tangent. They're widely, you know, I think most people call them cosh and tangent. It's only the sine or sinh that's got some controversy. And tangent is just as you expect. It's sine of theta over cosh of theta. And that's clearly going to be e to the theta minus e to the minus theta all over e to the theta plus e to the minus theta. Okay. And now we have our perfectly well defined hyperbolic trig functions. And now there's various remarks on here. So, remark 1, there are reciprocal hyperbolics as expected. So, cosec, hyperbolic cosec of theta is just going to be 1 over sine of theta. Coth, hyperbolic cotangent, is 1 over tangent of theta. And sec of theta is just 1 over cosh of theta, as you'd expect. Okay. They're mainly by definitions, to be quite honest. Nothing to do with necessarily proving, they're just conventions that we're going to use. 2, what does... Well, okay, put it this way. With all the normal trigonometric identities, we use something called Osbourne's rule. And Osbourne's rule states the following. If a trigonometric identity has a product of sines or implied product, then change the sign before that term. Okay, so I'll give you, oh, I've run out of space. So I'll give you an example of that. Show you what I mean. Mate, what's going on? So, okay, so example of that. Let's look at our normal trig identity of the basic one, cosine squared x plus sine squared x equals to 1. So this will become, in the hyperbolic case, cosh squared of x But now because sine squared is sine times sine, this will become a sine squared of x, but the sign in front, plus, is now going to change to a minus that equals to 1. I'll give you another example. Cos of 2x equals 1 minus 2 sine squared of x. So naturally, cosh of 2x is going to become, and this is a triple equals sign because it's true for all values of x, 1 plus 2 sine squared of x. Okay, so these are examples when sine is explicitly being made a product of. But what if it's not? Well, let's look at the other one. Well, let's suppose I've got 1 plus tan squared of x equals sec squared of x. Well, the 1 stays the same. Sec squared will become sech squared. Now that's just 1 over cosine squared, so that's not going to change sign. But because tan is sine over cos, that's going to be sine squared over cos squared, so you've got a product of sines here, so this is going to be 1 minus tanh squared x. Okay, so being able to know your trig identities is going to help you massively when it comes to hyperbolics. And the golden rule is, which is Osbourne's rule, that if there's a product of sines, then you need to change the sign before it. If you want to prove why that's the case, then I suggest you write down what the identities are in terms of sine and cosine from first principles, i.e. sine is e to the theta minus e to the minus theta all over 2, and cosh is e to the theta plus e to the minus theta all over 2, and then expand it and see what happens. You'll see that that always is the case. But you're welcome to explore. Okay, third remark is, what does the plots of y equals sine of x, what does y equals cosh of x look like, and what does y equal tanh of x look like? Well, y equals sine of x is going to kind of look like a cubic, like that, and it's going to cut through the origin like so. This is x and this is y. Okay, so this is the plot of y equals sine of x. If you want to substitute in numbers, that's absolutely fine. You can prove this for yourself. It's not a problem. Cosh of x is going to kind of look like a U-shaped parabola, but it's a very different shape. It's going to cross the y-axis at 1. So this is the y equals cosh of x graph. And this is actually called a catenary. And it's not a parabola. If I was to draw a parabola on top of it, the parabola would be kind of more pronounced, looking like that maybe. So what is this catenary shape? Imagine it's like a drooping chain. Okay, if you was to have a chain or a piece of rope and hold it, one end in each hand, then that natural sag is the hyperbolic cosine function. It's not the same as a parabola. Now, what does the tan function look like? Well, we've now got enough information to piece this together ourselves, because we know what the sine function looks like for all values of x, and we know what the cosh function looks like for all values of x. So, what do we know straight away? Well, I know that when x is negative, sine is negative, and cosh is positive. So I know a negative divided by positive is going to be a negative down here. I know that when we're on the origin, we're going to have a 0 divided by 1, so it's going to go through the origin. And then on the right hand side, I've got a positive divided by a positive, so that's going to be positive as well. But how do we know it's not going to do something like this, or something like this, where it's bounded, say, between two values. For example, like the Arctan function. Well, let's have a look at what's actually going on and see if we can piece something together. So, tan of x, what is that? That is e to the theta minus e to the minus theta all over e to the theta plus e to the minus theta. Well, if I times everything by e to the theta top and bottom, I'll get e to the 2 theta minus 1 on the top, and I'll have e to the 2 theta plus 1 on the bottom. Not bad. And now, if I imagine that this was a plus 1, I would need to minus 2 up here so that the net result is a minus 1 on top. This means I can split this up as e to the 2 theta plus 1 over e to the 2 theta plus 1 minus 2 over e to the 2 theta plus 1. Right, so what's going to happen here? Well, I've clearly got the same top and bottom, so this is a 1, so I'm actually left with 1 minus that thing. So I'm left with 1 minus 2 over e to the 2 theta plus 1. Now, here's the deal. Because e to the 2 theta is just e to the theta all squared, look what happens. When I let theta, or x, tend to infinity, then this fraction is going to tend to 0 because I'm doing 2 divided by a massive number. Okay, so that tends to 0. But when I let theta equals negative infinity, what's going to happen? Well, it's going to be 2 over essentially a positive number that's massive. Well, is it? Well, e to the negative infinity is going to be 0. 0 squared is 0. So we're going to get, so when theta tends to infinity, then the y value, if this is y equals this thing, the output of it, well, that's going to be 2 over a massive number, which is 0, so it just tends to 1. And when theta is negative infinity, I'm going to get 2 over 0 plus 1, which is 1, and 1 minus 2 means that y is now minus 1. So in actual fact, we're going to get a curve that's trapped between 1 and negative 1 in the y-axis, and it hugs that for extreme values of x. It looks like this. So it kind of does actually look like the arctan function. Okay, other results. So where are we? Remark 4. What do we do with calculus? Well, do you remember that sine x differentiates to cosine x, which then differentiates to negative sine x, which then differentiates to minus cosine x, and then differentiates back? Do you remember that this is what's happening with respect to x as we're going round? Whoops. And integrating, so recall, this was the case. Well, with hyperbolics, it's even easier. For example, sine of x just differentiates to cosh of x, and cosh of x just differentiates back to sine of x. The one thing I will say though is remember the chain rule. Whenever you're differentiating or integrating hyperbolic functions, please remember the chain rule. So for example, if I've got sine of 2x, differentiating that means that sine becomes a cosine of 2x, and then I must bring the argument out, so this actually becomes 2 lots of cosh 2x. I.e. you have to bring the argument out and then differentiate it with respect to x by the chain rule in the exact same way. Okay. Now you can probably think, what does tanh differentiate to? And it differentiates to much in the same way. Also remember Osbourne's rule. And if you want to prove that these are all the case, then just imagine you need to differentiate tan, which is e to the theta plus minus e to the minus theta. Well, we're doing it in terms of x now, aren't we? So it'll be e to the x minus e to the minus x all over e to the x plus e to the minus x. This is differentiated with respect to x. And you can do this from first principles if you want to. Otherwise, what you could do, let's say I wanted to differentiate hyperbolic tan. So tanh of x, which is going to be this thing. So it will be, remembering the quotient rule, v du, so v, which is e to the x, e to the x plus e to the minus x, times by du. Well, this is going to be e to the x because e to the x differentiates itself, and minus e to the minus x becomes plus e to the minus x, minus u, which is e to the x minus e to the minus x, dv. Well, clearly that's just going to become e to the x minus e to the minus x, and this is all over v squared, which is e to the x minus e to the minus x plus squared. Right. Well, there's lots of things you can do here. You could expand the top if you wanted to. You might as well. So I've got e to the 2x, and then e to the x times e to the minus x is e to the 0, so that's plus 2, plus e to the minus x, and then minus this other quantity, which is going to be e to the 2x, and then I'm going to have a minus 2 here, I believe. Yep, and then that's going to be a plus e to the, 2x? No, e to the minus 2x here. And this is all over e to the x plus e to the minus x squared. So what's going to happen is this e to the 2x will cancel with that e to the 2x. This is supposed to be e to the minus x because I've got e to the minus x times e to the minus x. So then this e to the minus 2x will cancel with that one. And I will get 2 minus a minus 2, which is 4 on the top, all over. And then I won't expand that because it's e to the x minus plus e to the minus x squared. And then if I think about this very carefully, this is actually the quantity squared of 2 over e to the x plus e to the minus x squared, and this is clearly 1 over cosh of x. So this is clearly sec x, and it's sec x squared, just as you'd expect tan to differentiate to sec squared, tanh differentiates to sec squared. So as long as you know your Osbourne's rule for trigonometric rearranging, that kind of thing, you'll be okay. Now, there's other remarks as well, and to do this, let's have a new one. No, where are you? There. So where are we? Remark 5. Okay, remark 5 is inverses of hyperbolics. So let's suppose I want the inverse sine of x. I want to apply the inverse sine of x. Well, these are given to you in the formula booklet. So always check them. You're not supposed to know these. This is going to be the natural log of x plus the square root of x squared plus 1. The inverse hyperbolic cosine is ln of x plus the square root of x squared minus 1. And the inverse hyperbolic tan function is 1/2 of ln of, and it's this horrible fraction, 1 plus x over 1 minus x. And by the way, when you see something like this, or r tanh, when they've got the r's in front of them, that's just the inverse. So another reason why I like to call sinh shine is because you can then say r shine. It just sounds funny to say arse shine, but never mind. Please notice that the formula booklet, and I'll put this in point 6, the formula booklet also gives useful derivatives and integrals that you might need in a pinch. And if you want to prove these, same with the hyperbolic, all you need to do, the inverses. If you want to prove the inverses are true, just rearrange to make x the subject. I.e., if you've got x, if you've got say y equals e to the x plus e to the minus x over 2, where y equals cosh of x in this case, then you just need to make e to the x the subject. So I don't know, maybe you'd times both sides by e to the x to get y e to the x like this equals e to the 2x plus 1 over 2, times both sides to make that a 2, minus the e to the 2x to that side, so that's 2y e to the x minus e to the x, and that equals to 1. Take a factor of e to the x out, so this is 2y minus 1, this equals to 1. You know, lots of things going on here. This is a 2. This is an e to the 2x, isn't it? Yeah, you just play around with this, to be quite honest. And you well, no, that's not going to factorise, is it? What you would probably do actually is you'd complete the square on this thing. So times everything by minus 1 to get a minus 1 there. That's e to the 2x, and this is going to be minus 2y e to the x. So you'd have e to the x minus y, and then that's squared, and then minus that thing squared, which is y squared equals to minus 1. You'd add y squared to both sides, so y squared minus 1 is that, so you've got e to the x minus y squared. You'd square root both sides, so the square root of y squared minus 1 plus or minus, and then this equals e to the x minus y. And then you'd have e to the x equals y plus or minus the square root of y squared minus 1. And then you take the natural log of both sides, so x equals ln of y plus or minus the square root of y squared minus 1. And you'd take the positive root. And the reason why you would take the positive root, let's think about that. If you took the positive root, you are, one, you're making sure that you want to take the logarithm of a positive number. Yeah. And what you could have done actually is you could have taken this value for y, whatever it be, and if you use the minus value and you plugged it into the original, I don't think you'd get the same thing. But you can work through this more formally, but essentially that's what you'd need to do to prove the inverses. You don't have to do it, but it involves completing the square. And the same thing with derivatives and integrals, you just have to do it from first principles. But I've already talked about what sine, cosh and tanh differentiates to. But if you wanted to differentiate r sine of x, the inverse sine of x, that's a nice one because that's 1 over the square root of x squared plus 1. So that's really nice. So that means whenever you have to integrate 1 over the square root of x squared plus 1, that's just r sine. R cosine of x, if you differentiate that, that's just going to be more or less the same thing, but it's going to be x squared minus 1. And then differentiate r tanh of x, that is going to be 1 over 1 minus x squared. So that's really, really nice. There's other integrals and stuff that you can know how to do. For example, if I wanted to integrate tanh of x dx, that's just ln of cosh of x plus c. more or less the same things really. Look in the formula booklet, it's not that deep. There's various things you can do with hyperbolics, but that's pretty much all I wanted to talk about. And sometimes they're really good for substitution. For example, so by substitution for integrals, generally speaking, when you can see a 1 plus x squared, you want to use a hyperbolic, because you want to abuse the fact that cosh squared of x equals 1 plus sine squared of x. Whereas if it's a 1 minus x squared, then you want to use a normal trigonometric function, because you want to abuse the fact that cos squared equals 1 minus sine squared. So, Now there's a whole load of things to talk about with hyperbolics. For example, and when we talk about de Moivre's theorem, essentially, the hyperbolic functions are essentially derived from inputting a complex value into the normal circular trig functions and playing around with de Moivre's theorem. And again, when we get to that, I really implore you to go away and try it for yourself. But really, I just want to get behind the mechanics of what the hyperbolic functions are. The fact that they're relatable to the trig functions through Osbourne's rule, how to differentiate them, what the curves look like, how to deal with curves, how to integrate, how to differentiate, and how to solve hyperbolic functions. So what I'm going to do is I'm going to give you guys a little bit of time to try this one, and then we'll go through it. So just pause the video and we'll come back. Okay, so solve the equation 7 sec x minus tanh of x equals to 5, and give your answers in the form of ln a, where a is a rational number. Okay, so first thing I'm going to try and do is write this in terms of sine and cosine. So 7 sec is 7 over cosine of x, and tanh is sine of x over cosine of x, like so, and this equals to 5. Okay. I can get this over a common denominator because they're both denominators of cosh x. So this is 7 minus sine of x all over cosh of x, and this equals to 5. If I multiply by cosh of x, I will get 7 sine of x equals to 5 cosh of x, like so. Well, there's not a lot I can do here, so I think I'm just reduced to writing out sine of x and cosh of x in terms of their exponentials. So this will become 7 minus sine of x, which is e to the x minus e to the minus x all over 2, equals 5 cosh x, which is 5 lots of e to the x plus e to the minus x all over 2. Expanding this out really carefully gives 7 minus e to the x over 2 plus e to the minus x over 2 equals to 5 e to the x over 2 plus 5 e to the minus x over 2. Well, if I subtract e to the minus x from both sides like this, I'm going to get 4 e to the minus x, which is just 2 e to the minus x. And if I add e to the minus x, e to the positive x over 2 to both sides, then this will become 6 e to the x over 2, which is 3 e to the x. And this will equal to 7. If I then subtract 7 from both sides, I will get this. And then to make things more concrete, if I multiply both sides by e to the x, I'll get 0, and then 3 e to the 2x, plus 2 minus 7 e to the x. And then if I make the substitution, let u equal e to the x, then this becomes 3 u squared plus 2 minus 7u equals to 0. Or in a more familiar way, 3u squared minus 7u plus 2 equals to 0. And now we've got a nice quadratic to solve. So, does this factorise? Well, I think if we have 3u and then u, and then I make this a -1 and a -2. I think that works. Nope, that doesn't. Other way around. Yeah, because 3u times -2 is -6. There and there is minus another 1, so it's -7. 3u times u is 3u squared, and -1 times -2 is +2. So we're now going to have the two solutions are, from this bracket, u equals 1/3, or from this bracket, u equals 2. And remember, u is e to the x, so that means e to the x equals 1/3, or e to the x equals to 2. So if I take natural logarithms of both sides, that means x equals ln of 1/3, or x equals the natural log ln of 2. And yeah, because there isn't any funny things going on, like dividing by 0 or multiplying by 0 anywhere, then we're perfectly fine to do this. So yeah, those would be my answers for that question. Okay, next question. Pause the video, give it a go yourself. Okay, starting from the definitions of sin x and cos x in terms of exponentials, prove that this is the case. Right, well, it's explicitly telling me to do something, so maybe I should do it. So, cosh of 2x is just the cosh function, but replace x with 2x. So, that's going to be e to the argument, which is 2x, plus e to the negative argument, which is 2x, and this is all over 2. And this is supposedly equal to 1 plus 2 lots of sine squared x. Well, sine is e to the x minus e to the minus x all over 2. Okay, so let's look at the right hand side. I've got 1 plus 2 lots of. Now let's square what's in here. Well, on the bottom, 2 squared is just 4, so that's easy. And if I square the top, I've got e to the x minus e to the minus x squared. So I'm going to have an e to the 2x. I'm going to have a minus 2, because I'll have e to the x times that, and then the other way around from the double brackets, because remember I've got e to the x minus e to the minus x times by itself, looking like that. Then finally I'm going to have plus e to the 2x, but negative over here. So what's going to happen? Well, the 2 and the 4 will cancel to make a 2 there. And then the 1 is technically a 2 over 2. So I'll add that to the e to the 2x minus 2 plus e to the minus 2x. And then this is all over 2 as well. And then clearly, because they have the same denominator, this minus 2 is going to cancel with that 2. So I am just left with e to the 2x plus e to the minus 2x all over 2. And that is the same as what I wanted from the left hand side, so that's done. And again, this is like when I was saying, like, I'm not going to go through everything of the Osbourne's rule, because sometimes it's just nice to work through them. And to be honest, they're often exam questions, because, you know, exam boards are pretty lazy sometimes. But if you want to feel particularly well prepared, then go for it. Part B, solve the equation cos 2 of x minus 3 sine of x equals to 15, giving your answer as exact logarithms. Well, I've just spent the first bit of the question turning cos 2x into something else, so maybe the question's trying to get me to do the same here and turn that cos 2x into something else. So I'm going to replace it with 1 plus 2 sine squared of x, and then minus 3 sine of x equal to 15. If I minus 15 from both sides, I'm going to have 2 sine squared of x minus a 3 sine of x, and I believe I'm going to have a negative 14. This appears to be a quadratic, so if I let u equals to sine of x, then I've got 2u squared minus 3u minus 14 equals to 0. Does this factorise? Let's give it a go. Well, to check if something factorises, then b squared minus 4ac has to equal a square number. B is minus 3, so that squared is 9, minus 4 lots of a, which is 2, lots of c is minus 14. Well, that becomes a plus 8 times 14 It's 32, 8 times 1 is 8, plus that is 11. 112 plus 9 is 121. 121 is square, so this most definitely factorises. So because 2 is prime, I'm going to let that be 2u and this be a single u. Silly boy. And then I'm probably going to make that a minus 2 and this the plus 7. The reason for that is, no, I'm going to make this the minus 7 and that the plus 2. The reason for that is minus 7u is minus 7u, but then 2u times 2u is 4u, and minus 7 plus 4 is the minus 3. Everything else seems to work out by inspection. So either u is going to be 7/2, or u is going to equal minus 2. So that means I've got sine of x equals to 7/2, or I've got sine of x equal to negative 2. But that's not the end of the story, because I should have what my inverse sines are. Where are they? Over here. So I'm going to copy this, bring it down. So my inverse sine, so this is going to become x equals, and to inverse sine both sides I have ln of the input, which is 7/2, plus the square root of the input squared, which is 14/4 in this case, plus 1. And then for this one, I'm going to have x equals the natural log of the input, which is minus 2, plus the square root of the input squared, which is 4, plus 1, so that's 5. So actually this one is simplified already, because that's just root 5 minus 2, or minus 2 plus root 5. That's positive, so that's going to be okay. This one looks a bit nastier. Upon closer inspection, this is going to be x equals ln of 7 plus root 53 all over 2. The reason for that is because 1 is 4/4, and 4/4 plus 49/4 is 53/4. I can take the over 4 out as a factor, and that's over 2, and it's going to simplify down quite nicely to this. So those are my two answers as simplified exact logarithms. Coolsies. Right, next question. If you want to pause the video, give it a go yourself. Okay, so given that f of x is that, as above, show that f of x is also written as that. Well, I think you just have to write down from first principles what's going on. So f of x is 5 cosh of x, so that's 5 lots of e to the x plus e to the minus x over 2, minus 4 sine of x, which is e to the x minus e to the minus x all over 2. Clearly, you're going to have 5 lots of e to the x there, minus 4 lots of e to the x, both over 2. So this is going to be a single e to the x over 2. And then you've got 5 e to the minus x over 2, and then minus 4 lots of minus e to the minus x. It's going to be plus 9 of e to the minus x over 2. This can clearly be factorised to a half of e to the x plus 9 e to the minus x. So that's not that big of a deal. Solve f of x equals to 5. Well, that's quite easy, because if a half of e to the x plus 9 e to the minus x equals to 5, I can times by 2 to get e to the x plus 9 e to the minus x equals to 10. I can subtract 10 from both sides to get e to the plus x minus 10 plus 9 e to the minus x equals to 0. And then times by e to the x both sides to get e to the x all squared minus 10 e to the x plus 9 equals to 0. And this is clearly a quadratic in e to the x again. You can do a substitution if you want, or you can just jump straight in and say it's e to the x minus 1 times e to the x minus 9. So either x is going to equal the natural log of 1 when I do e to the x equals to 1, then log both sides, so that means x is 0, or e to the x equals to 9, which means x will equal the natural log of 9. So there's two values that x could be for that. Okay, show that the integral of that thing equals pi over 8. Okay, so now why don't we just play around with this and see what we get. So the integral of ln 3, and then a half ln 3 is technically ln of root 3, and then 1 over 5 cosh of x minus 4 sine of x is just f of x, and I know it's this thing. So 1 over a half means I can put the 2 up top there, and then this becomes e to the x plus 9e to the minus x, and then this is dx. Okay, not particularly nice. How about we multiply by e to the x top and bottom, so this becomes ln 3 times root 3 like this, and this becomes 2e to the x all over e to the x all squared plus 9 dx. Okay, now if we let the substitution let u equals e to the x, then du will be e to the x dx, and I can spot that this ex and dx will cancel just to give a du. So immediately we're in business, we've just got a du there, this is a 2, and then on the bottom, since u equals e to the x, I'm just going to have u squared plus 9 on the bottom. And funnily enough, an integral of 1 over something squared plus 1, I believe we talked about before. Where is it? Where is it? Did I not write it down? Really? Well, you look in the formula book for that kind of thing. Just trying to think if I've got it written down anywhere here. No. Okay, well, I'll tell you what, I'll show you the formula booklet and we'll go hunting for it. We need to change the limits though. So when x equals to ln 3, then clearly u is just going to be 3 because we exponentiate it. And then when x equals ln of root 3, then clearly u is root 3, so we're going to have root 3 on the bottom. Okay. Well, what can we do now? So, what we can do is if I look up in the formula sheet, add Excel formula sheet, add Excel formula booklet, and I look at the latest one, issued in 2017, and I'm going to look for some standard integrals, because I know there's one for 1 over 1 plus x squared. Where is it? There you go. Right. Okay. So I've got that the integral of 1 over x squared plus 1 dx is just arctan of x. That's important. And we kind of got that thing going on, except this isn't a 1, it's a 9. So we're going to have to play around with this a little bit, but that's okay, we can do with that. So what I'm going to do is I'm going to take the 2 out as a factor, so there's a 2 out here, and this is a 1. And then what I'm going to do is this is still between root 3 and 3, that's 2, and this is 1 over. And now, if I take a factor of 9 out of the bottom, I'm going to technically have u over 3 squared, thinking about it, because it's u squared over 9, and then this becomes plus 1 du. And now I can take the 9 out, so this becomes 2/9 of 3 between root 3 of 1 over u over 3 squared plus 1. And now we just need one more substitution, so let v equals u over 3, so that dv equals du over 3, or I can times by 3 both sides to get 3 dv equals to du. And well, if u equals to 3, then v is going to equal to 1, right? Because 3 divided by 3 is 1. And if u equals to root 3, then v is going to be root 3 divided by 3, which is 1 over root 3, I believe. So this will become 1 on the top, 1 over root 3 on the bottom, 1 over u over 3 is now v squared plus 1. And then du is now 3 lots of dv. But then this is being times by 2/9. And the 3 and the 9ths will cancel, so this will become 2/3. Okay, if I'm going too quickly, I apologise, but you need to, well, your substitution must be pretty good, and it needs to be. I now know what the integral of 1 plus my variable squared, 1 over my variable squared plus 1 is, so this is going to become arctan of v between 1 and 1 over 3, and this is times by 2/3. So this is going to be 2/3 of, well, what's arctan of 1? Well, arctan of 1, I believe. What's the angle you're going to get when the opposite and adjacent are the same? That's going to be pi over 4, isn't it? Minus, and what's arctan of 1 over root 3? I believe that's pi over 6. So, over a common denominator, I'll just work upwards for a little bit. Over 24, this is 6, well, I can get this into 12s actually, can't I? This is going to be 3 pi 12ths minus, and pi 6 is 2 pi 12ths, so this whole thing becomes pi over 12. So what is 2/3 of pi over 12? The 2 and the 12 cancels to a 6. 3 times 6 is 18, so this becomes an 18th of pi, which I believe is what we wanted to show. Bosh. Done. So yeah, not so bad. Just needed a few substitutions, and it wasn't actually that bad at all. Okay, next up, inverse tanh. Pause the video, give it a go yourself. Okay, prove the inverse tanh is that thing. Okay, stating the value of the constant k. Okay, well, I mean, spoiler alert, we know the graph. We know that this, oh man, just got my iPad all wet. We know that the inverse tangent function is, well, it's going to have limiting values. We're kind of guessing it's between 1 and -1. But let's give it a go. Why must it be between 1 and -1? Well, because if x was lower than -1, this thing would be positive, sure, but 1 add something lower than -1 would make the whole thing negative, and you can't take the logarithm of a negative number. So that's going to fall apart. Similarly, if 1 is bigger than x is bigger than 1, then I've got 1 plus a number bigger than 1, so I've got a number bigger than 2 on the top. But 1 minus something bigger than 1 is going to make that negative. So you're going to have something bigger than 2 divided by a negative, which is going to make the whole thing negative. So yeah, it's not going to work. So straight off the bat, you can tell straight away it's between 1 and -1. If I want the inverse tan function, well, I just need sine, which is e of x minus e to the minus x over 2 divided by e to the x plus e to the minus x over 2. And if I set this equal to y, I now need to make x the subject. Lots of ways of doing this. I will probably times by e to the x top and bottom to get e to the 2x up there minus 1, and this is all over e to the 2x plus 1. I will do a similar trick as before, whereas I'll make this a plus 1 and remember to minus 2. So this whole thing becomes 1 minus 2 over e to the 2x plus 1, like that. What I will probably do now is do 1 minus y equals 2 over e to the 2x plus 1. I'll reciprocate both sides to get e to the 2x plus 1 all over 2 equals 1 over 1 minus y. I'll times both sides by 2, so that will become a 2. I'll then subtract 1, so this will be minus 1, and that will become this. I'll get this thing on the right hand side over a common denominator, so 2 over 1 minus y minus 1, which is 1 minus y over 1 minus y, will mean I'll have a 2 minus 1, which is a 1, and minus minus y becomes a plus y, so this becomes a 1 minus y on the bottom. This is going to equal e to the 2x. If I take the log of both sides, then I'll have ln of 1 plus y over 1 minus y equals 2x. And then if I halve it, then x equals a half of that stuff up there. So clearly this means the inverse function, the inverse tanh of x, is just a half of ln of 1 plus x over 1 minus x. I feel like my previous explanations gave the game away a little bit there, but there you go. So that's a fairly standard book proof actually. Sometimes they do this at A level, it's in the further maths course, but whatever. And the value of k I've clearly talked about there for the reasons I gave, because you can't take the logarithm of a negative number, and for x outside of those bounds, it's this result here would be negative when x is outside of these bounds, so clearly k is 1. Part B, hence or otherwise solve that equation. So I'm going to have to do the inverse tanh of 2x equals to the natural log of the square root of 2 minus 3x. And why did I put a 2 there? That's a 3. Well, I know what the inverse tanh function is because it just made me do it. So this is going to be a half of ln of 1 plus x over 1 minus x. And I'm going to put that half in using the log rule. So it's this. So it's now ln of the square root of 2 minus 3x on the other side. The reason I do this is because now I can take the exponent on both sides. Whoops. And now, essentially, I can square both sides. So I've now got this. And now this is something I can solve quite nicely, because now 1 plus x equals 2 minus 3x multiplied by 1 minus x. Expand the right-hand side. We'll give 3x squared because of that times that. Minus 3x minus another 2x is minus 5x. And then 2 times 1 is plus 2. Remember, this equals 1 plus x. If I subtract x from both sides, this is minus 6. And if I minus 1 from both sides, it's plus 1. Does this factorise? B squared is 36 minus 4 lots of a, which is 3 lots of 1. 36 minus 12 is 24. That's not a square number, so this doesn't factorise. So x is going to equal minus b, which is 6, plus or minus the square root of, I've just worked out what b squared minus 4ac is, so that's 24, all over 2a, which is 6. So x equals 6 plus or minus root 24, I believe that's 2 root 6. Yep, and then this is all over 6. So x is going to equal 1 plus or minus root 6 over 3. Yeah, and both of these are allowed, since 1 minus root 6 over 3 is definitely less than 1, but it's greater than minus 1, so that's okay. But 1 plus root 6 over 3 is not allowed, is it? Ooh. So the only solution, but 1 plus root 6 over 3, that doesn't satisfy this, because you've got 1 plus something. So I think the only solution, actually, is 1 minus root 6 over 3. I think that's the only solution we're allowed to do. I think they made that clear by getting you to think about what the inputs of that is. Well, you know, we could... Oh, we've got time. Well, what is tanh? Tanh is e to the thingy e to the x, but if that's a ln, so that's going to be root 2 minus 3x. And then this is going to be minus e to the minus that, which is going to be 1 over root 2 minus 3x. And this is all going to be over the same thing, 2 minus 3x plus 1 over root 2 minus 3x, like so. That's tanh, and this needs to equal 2x. If I get this over a common, if I times by root 2 minus 3x top and bottom, this is 2 minus 3x minus the 1 on top, and then this is over 2 minus 3x plus 1 on the bottom. So 2 minus 1 is going to be a 1, this is over minus 3x, and then 2 plus 1, so it's going to be a 3 minus 3x. Well, actually this isn't going to work, is it? Because if 1 plus root 6 over 3 is bigger than 1, then when you substitute it back into here, this is going to be negative, and you can't take the square root of a negative. So it has to be less than 1. So yeah, that's 100% the right thing. Okay. Pause the video, give it a go yourself. Okay, using a substitution that should clearly be stated, or stated clearly, show that the integral of f of x is a times the inverse sine of bx plus c, where c is an arbitrary constant and a and b are constants to be found. Okay, so ideally I'll remind myself the integral of what equals r sine of x plus a constant. So maybe if I look in the formula booklets, I'll see that it's actually the integral of 1 over the square root of x squared plus 1. So I've got a couple of jobs. 1, to make that 9 a 1, and 2, to make that 4 become a 1. Now what we're going to do is, generally speaking, you want to make the 9 become a 1 first. So if I take f of x, I realise this is 1 over the square root of 9 lots of 4x squared over 9 plus 1. And this is the same as 1 over 3, because I can square root 9, times by the square root of, and then 4x squared over 9 is 2x over 3 all squared plus 1. And now if I want to integrate this thing, then I just have that. I take the 3 out, so this is 1/3 of the integral of 1 over the square root of 2x over 3 squared plus 1 dx. And now to integrate this, all I need to do is let u equals to 2/3 of x, so that du equals 2/3 of dx, multiply by 3 over 2 to make 3 over 2 du equal to dx. And now we're actually going to have a half of the integral, because if you think about it, this 3/2 is going to be multiplied by the third when you take it out as a factor. And then it's going to be 1 over the square root of 2/3 of x, which is u squared plus 1 du. I now know that this is going to integrate to a half of r sine of u plus a constant. I now know that u is 2/3 of x, so this is actually going to be a half of, now I want it in that form, so I'm just going to put hyperbolic sine inverse of u, which is 2x over 3 plus a constant. So here my constant a is a half and my constant b is 2/3. And I believe I've answered the question for you. Okay, hence find in exact form in terms of natural logarithms the mean value of f of x over the interval 0, 3. Okay, now I haven't gone over this, but actually it's a really easy thing to do. I mean, for example, the mean value of f of x, what does that mean? Well, let's suppose I've got a rectangle like this. And it's a rather boring one, and this is my f of x function, and it's between, say, 1 and 3. Then what's the mean value of f of x in this case? Well, it's going to be the height of the rectangle, because we're going to abuse the fact that area is usually base times by height. And in general, it's this f of x is the height, and times by base is going to be the interval. Okay, now what happens if it's not a rectangle, i.e. it's a function looking like this, and it's between, say in the case of the question, between 0 and 3? Well, the interval is still going to be okay, that's from 0 to 3. The area is just going to be the integral, and now we're multiplying by the mean value of f of x. Because what we're essentially saying is the area divided by the width is going to be the average height, isn't it? So all I need to do actually is the mean value of f of x. Well, the area is going to be between 0 and 3 of f of x dx. And I have to divide by the interval width. Well, the interval width goes from 0 to 3, so that's 3 wide, so that's a third. So this is actually going to be the mean value of f of x. And generally speaking, if you want the mean value of a function over an interval, you just find the area by integrating it and then divide by the interval length. Because essentially the average height of a rectangle or an area, if you split it into rectangles, is always going to be the area divided by the width. Another way of looking at this is if I've got some finite area, which I'll designate as this green thing here, and I want to find the average y value of this, wouldn't it make sense that for that thing to have an average height, I could have also interpreted it as a rectangle with average height? And all we're doing here is we're saying the area of the pink rectangle must be the same as the green area under the curve, and clearly the average height is just width, it's just area divided by width, and we know what the area is, it's just an integral. So I now know what the integral of fx is. I've done it over here. So this is going to be a third of the integral of 1/2 of the r sine inverse of 2x over 3, and this is going to be between 3 and 0. Okay, I can take the half out, so this becomes 1/6 of, and then it's going to be inverse sine of, when x is 3, I've got 2 times 3, which is 6 over 3, so that's 2, minus, and then inverse sine of 0. Now I know the inverse sine of 0 is 0, because it goes through the origin, the original graph. If I look at the sine of x graph over here, look, it goes through the origin. So I know that sine of 0, I know that sine of 0 is 0, and I know that inverse sine of 0 is also 0 just by considering the graph. So that's not really going to be too much of a problem. So this thing disappears. However, what is the inverse sine of 2? Well, I'm just going to borrow my inverse sine function over here again. And that's just going to be a natural logarithm. And I'll just figure that out right now. So it's going to be, remember, we've got this thing going on. It will be 1/6 of ln of the function, which is, or the value, the input of inverse sine is 2, plus the square root of 2 squared plus 1, which is 5. So actually, the mean value of this function is 1/6 of ln of 2 plus root 5. And yeah, that actually wasn't too bad. Okay, now the last question I put here is a step question. So if this does take me half an hour, 40 minutes, and I do stumble and I get lost, please don't get mad. This is supposed to be a very difficult question. I'm just trying to think whether it was from step 1, 2 or 3, so we can figure that out right now. So let's have a look at hyperbolic functions. Yeah, so the step, if you just Google step questions by topic, this will come up. It's an incredibly good website, I find. Where is it? Yeah. Okay, so this is a step 3 question from 2014. That's probably why I chose it. So step 3 is traditionally like a really hard paper to do. If you can do a step question in half an hour, you're doing really well. I'm probably going to take about 40 minutes or so. If I do it quicker, well done me, but it's not really proving anything. Okay, let's just crack on with it. So, show by means of substitution that u equals cosh x, that integral evaluates to that. Okay, well if u equals cosh of x, then du by dx is going to be sine of x dx. That's nice because I've got a sine x dx here, so I know that term's going to disappear. So all I have to do now is write cosh 2 of x in terms of cosh x, which I believe is 2 cosh squared x minus 1. Okay, well that's not too bad. So this means this integral is going to become just 1 over 2 cosh squared x minus 1 dx. Yeah. That's pretty much it. Okay. Where to move forward from here, though? Well, you could split this up into partial fractions, I suppose. Do I want to do that, though? Because 2 cosh squared x minus 1 is the same as root 2 cosh x minus 1 times by root 2 cosh x plus 1. So if I just treat cosh x as my entity a, then I've technically got root 2a minus 1 times by root 2a plus 1. So this will actually mean that I've got 1 over the two brackets equals, let's call capital A the one that's over this, that would be root 2 little a plus 1, plus b lots of root 2a minus 1. So it looks like by comparing the coefficient of a's, that I've got capital A plus b equals to 0 because I've got none of them, and then I've got a minus b equals to 1. It looks like a equals a half, and it looks like b equals minus a half. I'm going to add the two together, I'm going to get 2a there, and 2a equals 1, and then a half plus what is 0, that's minus half. So it looks like I have to integrate a half lots of 1 over root 2 cosh x Oh, what am I doing? What am I actually doing? This is just 2u squared minus 1, isn't it? Am I being such a silly? That's 2u squared minus 1. And this is du. So it'll be a half of 1 over root 2u, and then the first one was a minus 1, and then minus 1 over root 2u plus 1 du. Well, if I artificially multiply these fractions by root 2 and then divide by root 2 on the outside, then I realise that I've got 1 over 2 root 2 of, and then since the bottom differentiates to the top, I've got ln of the bottom, so ln of root 2u minus 1. And by the way, that's maybe I should put u root 2 there, just because otherwise it's going to get confused. And then minus ln of u times root 2 plus 1. So this is going to be 1 over 2 root 2, lots of the natural log of, and then this is going to be root 2u, which is root 2 cosh of x minus 1, over root 2u, which is root 2 cosh of x plus 1 plus a constant. So I'm guessing that's what I was supposed to be going for. 1 over 2 root 2, lots of the natural log of root 2 cosh x minus 1 over root 2 cosh x plus 1 plus a constant, bosh. Okay, fine. Not a problem. Smoothish sailing. I have to do a similar substitution for now cosh of x over cosh of 2x. So let's take this for part 2. So okay, let's do a similar thing. So for part 2, I've got this integral. Well, how about we let u equals to sine of x, so that when we take du by dx, we're going to get cosh of x dx like that. And I know that this is going to cancel. So this is going to be integral of 1 du. But now, cosh 2x in terms of sine x is 1 plus 2 sine squared x. So it's going to be 1 plus 2u squared. So this is going to be 1 plus 2u squared du like that. Okay. So I think maybe I can do another substitution, because I want this to be some, well, 2u squared is the same as root 2u all squared. And 1 plus something squared on the bottom, I know how to deal with that because I've done it before. And I know that, where is it? I know that the integral of 1 over 1 plus something squared dx is arctan of x plus a constant. You know, remember we've done this stuff before. So if I can isolate that thing to just a 1u squared, that's fine. So how about we let v equals root 2 lots of u, so that dv equals root 2 lots of du. So then that means du is 1 over root 2 lots of dv. So this is going to become 1 over root 2 lots of dv. And then this becomes 1 over 1 plus u squared dv. Nice. So actually this whole thing becomes 1 over root 2 lots of arctan of x of the thing, which is v, plus a constant, and arctan v is root 2u, so that's actually root 2u, which is sine of x. Wow, plus c. I wonder if there's an easier way we could have done this. Well, that's technically legit. 1 over root 2 arctan of root 2 sine x. Does it simplify? Maybe. Is there an arctan function lying around? Nope. We just have to leave it as that. That'll do for me. That's technically a solution. I found as an expression for that. It's not necessarily the same as what you've got above. It's because we've got a different integral now. Yeah. Okay. Right, part 3. Using parts I and II above show that this is the case. So I want to integrate between 1 and 0, 1 over 1 plus u to the 4 du. Interesting. Okay. Right. how's this going to work? So what have I got to play with? I've got, I've got sine of x over cosh of 2x. So I know that integral, and I know the integral of cosh of x over cosh of 2x dx. When I did the substitutions, I think this one turned into the 1 over 2u squared minus 1 du. And using another substitution, this one became a 1 over 2u squared plus 1 du. Not immediately obvious how I'm going to times these two things together. I mean, if I add them together, what's going to happen? Well, I'm going to have 2u squared plus 1 plus a 2u squared minus 1 all over a 2u squared minus 1 times by a 2u squared plus 1. So that they're going to cancel. I'm going to be left with 4u squared on the top, and I'm going to get a difference of squared, which is 4u to the 4 minus 1 on the bottom, which is not great. I wonder how this is going to work. Well, you know what? If in doubt, how about we just try and get it in terms of exponentials? Why not? What is there to lose? So if I let u equals e to the xa, then du is going to be e to the x dx. Maybe we can play around with this a little bit more. And then this is going to transform into, well, when u is 1, sorry, when x is, wait a minute. When u is 1, then this must be e to the 0, right? And then when u is 0, this must be minus infinity, because the exponential function looks like this. Okay, let me just double check I'm reading the right thing. Yeah, okay. Well, we can swap the limits back, it's not a problem. So what's going to happen is this whole thing becomes 1 over 1 plus e to the 4x, and then du is going to be replaced with e to the x, so then this whole thing up here is going to be e to the x dx. Right. How is that useful? Well, well, I'm aiming to have a cosh 2x on the bottom, and that's got some squared terms. So if I divide by e to the minus 2x, or I times by e to the minus 2x, sorry, then this integral is going to be e to the minus x, and then I'm going to have e to the minus 2x here, plus e to the 2x here dx. This looks promising, because what have we actually got here? Well, e to the 2x plus e to the minus 2x all over 2 is cosh of 2x. So if I times that by 2, then I've actually got 2 cosh of 2x on the bottom dx. and this is between minus infinity and 0. And then what will I have to do to get a minus, an e to the minus x on the top? Well, if I've got e to the x plus e to the minus x over 2, I've got some multiple of cosh x's, and I want to add some multiple of sine x's. So it's e to the x minus e to the minus x over 2. Clearly, it looks like if b was minus 1 and a was 1, then the e to the cos x's would cancel, and e to the minus x minus e to the minus x would be 2 e to the minus x over 2, so that cancels. So it looks like I've actually got cosh of x minus sine of x on the top. And now, if I take this half out, like so, wow, so all I have to do is just 1 minus the other. That's cool. Fine. So this is just going to be a half of the integral between 0 and minus infinity of cosh x over cosh 2x dx minus a half of the integral between 0 and minus infinity of sine x over cosh 2x dx. So it's just going to be half of one minus the other. Okay, so the first one, so I'm going to have a half of the first integral, so that actually becomes 1 over 4 root 2 times the natural log of, and then that becomes root 2 cosh minus plus, so root 2 cosh of x minus 1 over root 2 cosh of x plus 1, and then this needs to be evaluated between 0 and minus infinity, and then minus a half, lots of, and then the other one I worked out to be this thing over here, so that's going to be 1 over 2 root 2, lots of, arctan of root 2 sine of x, and then this needs to be evaluated between 0 and negative infinity. Oh boy. Right, so let's take the 1 4 root 2 out as a factor, and let's sub in 0 first. So I know that cosh of 0 is 1. So cosh of 0 equals 1. So this is going to be root 2, so this is going to be ln of root 2 lots of 1 minus 1 over root 2 lots of 1 plus 1. Okay, minus, and now let's have the infinity thing in there. Oh, Jesus. Okay, well, this is not going to be nice because we've got an infinity over an infinity. But I'm going to pull a trick here that you've seen before today. So if I've got root 2 cosh of x minus 1, that's the same as plus 1 minus 2. And then this is going to be over root 2 cosh of x plus 1, and this is going to be over this, root 2 cosh of x plus 1. So actually, this whole thing is just 1 minus 2 over, and cosh of x tends to infinity as x tends to minus infinity. Why is that? Well, because we've seen the graph earlier on, haven't we? It's this U-shaped catenary thing. So as x tends to negative infinity, it's clearly going to go to positive infinity. So that looks like it's going to be well behaved, because 2 over infinity, essentially plus 1, is just going to tend to 0. So that whole thing becomes ln of 1, which is just 0. So that's going to disappear. So it's a minus of 0, so that can go. So actually that disappears, and we're just left with this thing. Okay, minus 1 over 2 root 2, lots of. Now, the first bracket, we've got arctan of sine of 0. Well, sine of 0 is just 0. That's really well behaviourally defined, so that's just arctan of 0. So that's just a big fat 0. Minus, and then what happens? Root 2 of sine of negative infinity. That just means we're going to have arctan of negative infinity. And arctan of negative infinity actually is fairly okay. That's minus pi over 2. So it looks like, oh dear, we're going to have a lot of minuses going on. So if I was to tidy all this up, we're going to have 1 over 4 root 2, lots of ln of root 2 minus 1 over root 2 plus 1, minus 1 over 2 root 2, and then I've got a minus pi over 2, so this is a pi over 2 here. So I think the second term is going to become pi over 4 root 2. The first term is 1 over 4 root 2. That's ln of root 2 minus 1 over root 2 plus 1. So I'm definitely going to have a 1 over 4 root 2 out as a factor. And this is ln of root 2 minus 1 over root 2 plus 1 minus pi. That's probably not the form they wanted it in at all. Almost there. We've got the over 4 root 2 as a factor. Did I have a minus pi? That's interesting. I've got a minus pi popping out of here. That shouldn't be the case. That should be a plus, shouldn't it? Well, that's interesting. I'll tell you what. We'll deal with it in a second. Let's sort this thing out first. So I've got root 2 minus 1 over root 2 plus 1, which I can times by root 2 minus 1 over root 2 minus 1 over here. So this is actually going to become root 2 minus 1 squared over 1. So this will actually become 2 ln of root 2 minus 1. Then minus pi. And this will be 1 over 4 root 2. Now I don't think that's right either, is it? It's root 2 plus. It's almost like I've got the negatives. What have I done? Oh man, really? I should have done the cosh minus the shine. Oh man, really? Yeah, so this actually is the cosh thing, so that should have gone to the other side. Oh man, I'm such a mong. I'm such an idiot. Right, okay. Well, let's switcheroo this thing. So what's actually going to happen? Well, it's not going to change too much actually. All that's going to happen is this stuff goes over here, and then it's going to be minus this stuff. Because we've technically got this was the cosh stuff, so this should have gone over here. This is the shine stuff, it should have gone over here. Well, I know what this thing is going to be because you've got a minus minus, that's plus, that's going to be pi over 4 root 2. And I've got minus 1 over 4 root 2 ln of root 2 minus 1 over root 2 plus 1. And I can take this minus up as a factor, so this becomes pi over 4 root 2 plus 1 over 4 root 2 ln of, swap that, so it's root 2 plus 1 over root 2 minus 1. And then this thing, if I times by root 2 plus 1, top and bottom, to rationalise it, we'll just give root 2 plus 1 all squared over root 2 squared, which is 2, minus 1 squared, which is 1 squared, that cancels. So I've actually got ln of this thing, the 2 comes out the front. So I've actually got 1 over 4 root 2, lots of pi, plus 2 ln of root 2 plus 1. And now this, ladies and gentlemen, should be exactly what we want over here. Pi plus, yeah, bosh. That's exactly what we wanted. So how long did that take? Not very long. Cool. So yeah, that's pretty much. I mean, if you're solving this kind of hyperbolic trig stuff, you know, this was a step 3 question from 2014. I mean, you are well on your way to being a very good mathematician as an 18-year-old. You know, probably not like exceptional, like, you know, Terence Tao or other ridiculous maths geniuses, but for a general maths undergraduate, you're doing really well if you can do this stuff. Anyway, there you go. Hope you had fun. Toodaloo.